This week's class is about exploratory data analysis. It's a way of looking at data to make sure that you interpret it correctly, that you don't find a spurious correlation or make some bad statistics. And this is really important in the post-truth world, where people will deliberately manipulate data to give the result that they want and then share it on social media. And this is not a new thing. I found this book, Damn Lies and Statistics, on my bookshelf at work. This is 20 years old and shows that this has been a problem for many decades. So let's make sure that you don't produce some bad statistics, either for your assignment or for the rest of your university career.
This week's subject is exploratory data analysis, often also abbreviated to EDA. And I'll start off with a quote. Exploratory data analysis is a state of mind, a way of thinking about data analysis, and also a way of doing it. And you can see that quote is very old, from 1979, from probably a generation before you, and it's by the authors Hartwig and Deerling. It comes from their book, very short pamphlet on exploratory data analysis, which I'll get you to look at this week. And it's a classic. And the concept is that the more you explore a data set before you decide how to analyze it, then the more you will learn from it, the better you will understand it, and your data analysis will be more effective. It should prevent you from misapplying statistics or missing important components or trends in the data. And Hartwig and Deerling proposed two principles when exploring data. One is skepticism, and the second is openness. In the context of skepticism, they propose that you should be skeptical of measures which summarize data, since these can conceal or misrepresent what be the most informative aspects of the data. And typical summary statistics that you might be familiar with are things like the average or the mean and the standard deviation of a data set. Maybe they hide some more useful information within a data series. And the second is to be open to unanticipated patterns in the data, since they can reveal new and useful hypotheses and analyses. You will probably have already formulated some hypotheses about the data set that you're working on at the moment. But by exploring the data, maybe you can modify those hypotheses or develop new ones. I've included an example on the right-hand side. This is from my own research, and you can see the citation to the paper in the vertical on the right-hand side. And this is a data set of the properties of annually laminated stalagmites, a global synthesis. You might not know that cave stalagmites have annual growth layers, similar to tree rings. And you can measure the thickness of these annual rings in stalagmites, and you can work out all sorts of things about past climates and past environments. And we made a big global analysis of stalagmite growth around the world, and this top figure shows all of the data, and this is an analysis of how long stalagmites grew, how many years, the duration of the laminated sequences. And we did an exploratory data analysis as the first step, and we made one of these box and whisker plots, which shows the range of the data with some outliers and a median value and a mean value. This is the distribution of data. And if we just looked at the whole data on its own, we may have missed something important in the data set, which is from one region of the world, in Ethiopia, which is the bottom figure here, the stalagmites grew for a shorter duration. So you can see that distribution here is much shorter. Typically they grow for maybe 100 to 200 years in duration. And that allowed us then to explore the data set in more detail. We could have a new hypothesis about why stalagmites grow for a shorter time period in Ethiopia compared to the rest of the world. And if you want to know the answer, it's because Ethiopia is situated close to the East African Rift and it's highly tectonically unstable. So the chances are in Ethiopia, there'll be an earthquake and some earth movements that will change the water movement in the unsaturated zone, and it will mean the water will stop flowing to a stalagmite sooner than in other parts of the world. So that's the value for us. As an example for undertaking some exploratory data analysis, we built some new hypotheses so we could better understand our data set. Why is exploratory data analysis important then? So the first point is that it's important for you to explore the distribution of single variables. In the example I gave you in the previous slide, there was a single variable, and the variable was the duration of the laminated sequences. How many years did the stalagmite grow for? But the example might be soil lead concentration in Sydney, and you might have a whole distribution of soil lead concentrations from different soil samples. You need to explore the distribution of that variable. For example, you could look at the distribution and you can see, is it normally distributed, which means does it have a bell shape type curve, or does it have outliers and extreme values? Or is the data skewed? And almost all environmental data is not normally distributed. Almost all of it is skewed. And again, in the example on the right hand side, here you can see that the data set is skewed and there are a few values which are large. There are a few stalagmites that have grown for thousands of years and they bias the statistics. Are there outliers or extreme values in the data set? In the example on the right, there are three dots, 3 values that seem to be outside the range of the rest of the data. Sometimes there might be gaps in the data, and sometimes the data set may have multiple peaks. You might have a bimodal distribution. And in order to understand a data set, you can't just rely on a summary statistic as the mean or the standard deviation. If you had a bimodal distribution and you took the mean, it wouldn't be very meaningful because it would fall in between where the two groups of data sets are. You need to know the shape of the distribution, and the shape is best perceived visually. The second important role for exploratory data analysis is that it is a necessary step to first explore the relationship between different variables. For example, in the case of soil lead concentrations, this could be the relationship between the soil lead concentration and the distance from the nearest major road. Before you go straight into doing some statistics to see if there is a relationship between soil lead concentration and distance from the nearest road, you should look at the data, you should explore it, and investigate the relationship between the two variables. Software such as Excel these days makes it very easy for you to go and put in some data sets into a spreadsheet, click on a button, and fit a regression line or a correlation to a scatter plot. But what Excel doesn't do is tell you if that is an appropriate thing to do. The default correlation and regression is normally linear. It assumes a straight line relationship. So the first thing you can check with exploratory data analysis is the relationship linear? Is it suitable to apply a linear correlation to? Are there data clusters or gaps in the data set that may affect the stats that you use? And are there outliers in the data set? So on the right hand side, the top example here, we have two variables, so one on the x-axis, one on the vertical or the y-axis. These are just hypothetical data sets, so we don't know what they are. And here we have two clusters of data. So this could be one group here, this could be another group here, and you could fit a correlation through here and a straight line regression. But is it meaningful? Is there really a straight line relationship here, or is it just two clusters of data with a few outliers? Or what do you do about gaps in data? So here's the middle example. Again, there's some variable on the x, some on the y, and there's a certain x value where there's no data, completely missing. So we don't know what happens here. Maybe the data carries on in linear fashion up to here, and then these are outliers, or maybe it's curvilinear, we don't know. And then finally, we have outliers in the data set. So again, here we have one variable on the x, one on the y. It looks like we have a linear relationship, but there's two outliers that fit that trend and two more that don't. What do we do about these two outliers? And often you might think, we'll just delete them. There may be an experimental error or mistake, and maybe that's what you find. But maybe these two outliers are more important than the whole of the rest of the data set because they're telling you something else about something that you weren't expecting. So exploratory data analysis says you should explore the data using a scatter plot when investigating the relationship between variables, and this will prevent any spurious correlations or bad statistics. Finally, exploratory data analysis can help prevent the use of incorrect statistics, but it can't help with preventing the lack of common sense. So you still have to think about whether the relationships you're seeing are meaningful, which is why we've already discussed hypothesis testing. If you set up some hypotheses first, which are based on some understanding of the processes that you might expect to be taking place, then you should be able to eliminate spurious correlations. And I've given two examples here. So the two examples would produce a scatter plot where there's a straight line relationship between the two variables, but they're spurious. So the top example here shows from 2006 to 2010 the undergraduate enrollments in US universities in black, and the number of injuries relating to falling televisions in red. And there's a close correlation between them, but they're not related. It's just that both of those parameters relate to population growth. So as the population expands over time, and we've already seen that population growth is increasing rapidly, particularly in urban areas, then you would have increased undergrad enrollments with increased population, but also an increasing chance of injury related to falling televisions. The lower example for Sharknado fans is the relationship between tornadoes and shark attacks from 2002 to 2010. Again, there's a reasonable relationship here. Maybe 1 year doesn't fit so well. The tornado data in red goes between about 1,000 and 2,000 tornadoes a year. But the shark attack data is too small to do a correlation. There's either 0, 1, 2, or 3 shark attacks in a year. So the data set's too small to be meaningful. It looks like there's a correlation, but there really isn't. So you need to have some common sense. You need to have some hypotheses that would explain the data set, and you need to look at the data and make sure that the data is suitable for statistical analysis. And in particular, it mustn't be so small that it will produce a spurious relationship. What is happening in class this week? This week, you'll be in the teaching laboratory again, and you will have a chance to use exploratory data analysis on the urban pollution data collected in the previous weeks. The lab classes are becoming increasingly informal as we head towards the end of term, and you are aiming to produce your lab report. So the aim of this class is for us to be around to help you use exploratory data analysis to understand the distribution of the single variables that you're analyzing and the relationship between the two variables that you're analyzing. And your learning outcome includes an understanding of the importance of the use of exploratory data analysis as the first step in any data analysis. And in this case, to have experience in its application to an urban pollution data set. But the class is more important than just this course. These are skills that you should then take with you for all the courses that you're undertaking here at UNSW. What do you need to do before the class? Well, I'd like you to read Hartwig and Dierling's 1979 Exploratory Data Analysis pamphlet or book. It's a very old book. It's very short. It's a classic. Published in 1979, this is in the very earliest days of computers. And the graphs in the book are very basic. They really show the limitations of computing in the 1970s. However, the writing is just, I find, so clear. So I find this a very easy to read and convincing text, and that's why I recommended it here. I don't want you to read the whole thing. I'd like you to read the chapters, The Exploratory Perspective, the chapter looking at data distribution of single variables, and part of the chapter looking at data relationships between variables, and that's just the sections on the introduction and displaying relations and understanding relations and summary. What do you need to understand? There'll be a class test as usual, and that will test your understanding of why it is important to do an exploratory data analysis as the first stage of any data analysis, why you should explore the distribution of a single variable, and why you should use scatter plots to explore relationships between variables. And with that understanding, we will use the lab class to use different exploratory data analysis techniques to explore your data and test your hypotheses and come up with some sound conclusions.